Hello everyone, M-Tip. This is PCBSYNC. Let's say the antenna array used to deliver EV units of power, but by the time it reaches the other end, there's only zero point 0.5 left. Wait a minute, where did the remaining zero point 0.5 go? It didn't cross over into a parallel universe, nor did the engineer next door use it to power a coffee machine. Today, we're going to investigate this case of the missing video power. After eliminating myself, we've narrowed down the suspects to two. The first suspect is conductor loss, which is the second suspect is dielectric loss, which comes from the PCB material itself. If you imagine a high-speed signal as a sports car speeding down the road, the copper traces are like the road surface, while the dielectric material is more like air resistance. Both of these culprits quietly drain your energy. And here's the bad news: the higher the frequency, the more they take. Let's take a look at the first suspect. Just gain effect. When it's direct current, the current obediently flows through the entire conductor, just like a subway car with plenty of empty seats. Everyone can stand wherever they want. But as the frequency increases, the current gets picky about where it flows. It doesn't like going through the middle anymore. Everyone crowds toward the edges. It's like the escalators in a mall. There are clearly two sides, but everyone insists on squeezing onto just one. So, what does this mean? It means the area the current can travel through gets smaller, resistance goes up, and losses increase too. Remember this key point: the current doesn't like going through the middle, it just squeezes to the sides. This is what happens at high frequencies. If the skin effect wasn't troublesome enough, rough copper surfaces just make things even worse. Smooth copper is like a highway. Electrons can travel smoothly without obstacles, while rough copper is more like the cobblestone roads in an old town. You might wonder, even though it's the same distance, the electrons end up taking a much longer path, and the farther they travel, the greater the loss naturally becomes. So, why do high frequency PCBs prefer smoother copper? Because the smoother the road, the less energy is wasted. The second suspect is loss. A lot of people think that electrons just quietly pass through FR4, but that's not actually the case. There are many small molecules in the material, just like the audience at a concert. As soon as the music starts playing, everyone tries their best to keep up with the beat, but their movements always lag behind. As a result, they use up more energy, and that energy turns into heat, DF, which is also known as the high tangent delta. This is what happens when you can't keep up with the rhythm. The loss just gets worse. So, high frequency designs are increasingly favoring materials with low DDF because they don't have as much loss. Remember this: not all energy can keep up with the rhythm. Next, let's look at the most important chart of the day. It's the same PCB, the same 50 ohm line, and the same length. If it's operating at a certain frequency, the loss is only zero point 0.3 decibels, which means about 93% of the energy can still get through. But if you switch to a real signal, the loss shoots up to 3 decibels, which means only 50% of the energy makes it to the end. The other half has already turned into heat. With the same board, just increasing the frequency by 10 times can make the pain increase tenfold. Remember this: when the frequency increases 10 times, the heartache increases 10 times. Today, you only need to remember three things. First, the higher the frequency, the greater the loss. The better the material, the less waste. Third, the farther the light signal can travel in the same month. So the transmitted power doesn't just disappear, it simply changes form and eventually turns into those tiny, unnoticeable bits of heat on your PCB. Thank you.